We are on Unit 5, Notes 5, our 5th section, and today we are covering the Fundamental Theorem of Calculus, Part 2. We just did Part 1, we're going to do Part 2 today. And we also put in here, we're going to look at the average value of a function as well. Okay, let's start off with something that we are familiar with, hopefully. Let's consider a definite integral. This definite integral, the function is going to be 4t cubed plus 2t minus 3 dt. Okay, and the boundaries on this definite integral, the lower boundary is 2. The upper boundary, I'm going to make x. So I could put anything I wanted there. So this is, I can put any boundary I want up there, right? So this time it's just going to be an x. So let's go ahead and evaluate this definite integral. Okay, so we're going to begin with our antiderivative. So the antiderivative here will be t to the 4th times 4 over 4, which is 1, plus t squared times 2 over 2, which is also 1, minus 3t, and we're evaluating that from 2 to x. We begin with the top boundary and plug that in for our variable. So this will be x to the 4th plus x squared minus 3x, right? And then we subtract what we get when we put a 2 in for t, right? 2 to the 4th is 16, 2 squared is 4, 3 times 2 is 6, like that. I could simplify this a hair. This is 20 minus 6 is 14. Okay. So that is that antiderivative, okay, evaluated from 2 to x, okay? Now what I'd like to do is I'd like to come in and I would like to take the derivative of our answer. Let's take the derivative of our answer. So the derivative of our answer is equal to, okay, the derivative of x to the 4th is 4x cubed. Derivative of x squared is 2x. Derivative of negative 3x is negative 3. And the derivative of negative 14 is 0. So what we showed was that the derivative of this integral because this was equal to this, right? The derivative of this integral is equal to 4x cubed plus 2x minus 3. Do you see a pattern there? I hope so. Okay. Would this have been a different answer if this 2 had been, say, a 5 or a 3 or a negative 10 or some other number? If this had been some other number, this would have been that number, and when we plugged that number in for t, we would have gotten a different constant here. But then when we take the derivative of that constant, it'll be 0, right? So it doesn't matter what this lower number was, as long as it's a number. As long as it's a number, those will be equal to each other. The derivative of the integral gives you back your function. Okay? Let's take a look. Following the same pattern, what would this be? The derivative of an integral, let's say from 5 to x, sine of 7t plus 8t cubed plus 1 dt. Okay? What would that be? Okay, well, it looks to me like they just put the x in for all of the t's, right? So this would be sine of 7x plus 8x cubed plus 1. The 5 won't matter. So that's just it. That's just it. So we get this function of x. The derivative of this integral gives us a function of x. Okay, let's do another one before we generalize. Let's go from 3 to x this time. Let's say e to the cosine of 5t plus natural log of t cubed. We can get pretty crazy with these. Okay. This would be, again, derivative of the integral would be e to the cosine of 5x plus natural log of x cubed, and that's it. So we don't have to actually find the antiderivative in this case. In this case, you're not actually finding an antiderivative like we did up here. Okay? We're using what we know now about the derivative of an integral. Derivative of an integral, think they kind of cancel each other out. You're kind of left with your function that was in here. Kind of. Not quite, but kind of. Okay? All right, now let's consider this. Now let's consider another derivative of an integral. Derivative of an integral. This time, instead of going, I'm going to start with 3. My lower boundary is 3. My upper boundary is not going to be a plain x. This time it's going to be a 3x squared. And I could show you why what's going to happen happens similarly to how I did this problem, but I just want to go ahead and show you how to do these, okay? So this would be 5, let's make this function 5t plus 1, okay? So again, derivative of an integral, they kind of cancel each other out, okay? But this is not just an x. If it's not just an x, you don't just plug that in for the t and call it good, okay? Because this is not just an x. Think of this as a chain rule, all right? Think of this as a chain rule. We are going to begin by finding the derivative of this. The derivative of 3x squared is 6x. I'm going to put that up front so I don't forget it. After that, I'm going to multiply by, now, yes, do put in 3x squared in for every t in your function. So this would be 5 times 3x squared plus 1. Okay? Now you can also think of this 3 back here, since we're thinking of this as a chain rule, okay? You can also do now minus, now we go to the 3. We begin by taking the derivative of 3. What's the derivative of 3? Well, the derivative of 3 is 0. And then plug in 3 for your t. Of course, the 0 is going to rule over here, so that's why the bottom boundary, if it's a number, well, the top boundary, if it's a number, it'll just zero that out. But this is in general how you would simplify one of these expressions if, in general, regardless of what you had here. If it's a plain x, those are kind of the most simple ones. But you can also think, what's the derivative of x? Just 1. So we could have said, oh, that's that times 1, right? Okay? So the 6x is the derivative of 3x squared. The 0 is the derivative of 3. And then each of these pieces was when we plugged in. Plug in 3x squared for t. Here we plugged in 3 for t. It just didn't matter back here because of that 0. Okay? Let's do another. Let's take the derivative of, let's go from -2 to sine of x, e to the t squared dt. Okay? All right. We begin up on top. First of all, notice, derivative of an integral. That's special, derivative of an integral. After I teach this section, I have students who even if that derivative is not there, they want to do this process because it's so much easier than actually finding an antiderivative. You can only do this process if you're taking the derivative of an integral. Okay? That's important. All right. Start up at the top boundary. Take the derivative. What's the derivative of sine x? Cosine x. And now multiply that by plugging in sine x for every t in your expression, in your function. So e to the sine squared x. Okay? Minus the derivative of negative 2 is just 0. So this would be e to the 4, but it doesn't matter because that's just 0. Okay? So again, remember that this is the derivative of sine x, and this is plug in sine x for t. This is the derivative of negative 2, and then we would have plugged in negative 2 for t, but we just didn't need to. Okay, another one. What if we have an x down here and a 3x squared up on top? And we'll make this a 4t squared plus 2t plus 1 dx. Okay? Alright, well, we're going to start up at the top. Well, first of all, we notice derivative of integral. Derivative of integral, think. This is part of the fundamental theorem of calculus. Derivative of an integral. Okay? So we begin at the top and we take the derivative. 6x. Now we plug in 3x squared for every t in our function. So 4 times 3x squared squared plus 2 times 3x squared plus 1 minus. Now we go to the x. What's the derivative of x? 1. Now plug in x for every t. Okay? Derivative, plug in, minus derivative, plug in. Okay? Start at the top. Alright. Fundamental Theorem of Calculus, Part 2. Okay, here's what it says. The derivative with respect to x of an integral. Okay? I'm going to make this integral, the function is just, I'm going to make it f of t, so f is some function of t. Okay? I need to make both the top and the bottom, for this general theorem, I need to make both the top and the bottom boundaries functions of x, general functions of x. So we can call them anything we want. I think I'm going to make this bottom one h of x and the top one g of x. Okay? But these are just like functions of x. Maybe it's sine x, maybe it's 3x squared. It could be just a number, right? Like 2 or 5 or something like that. But in general, these can be functions of x. This is equal to, we start at the top and take the derivative, so g prime of x. And then we plug in g of x for every t in our function. So f of g of x. Okay? Minus. Now do the same for h of x. So derivative of h of x times f of h of x. Fundamental Theorem of Calculus, Part 2. Derivative of integral. Derivative of integral. Okay, so think about this real quickly. This is important. Okay, think about this real quickly. today, for this part of the theorem, we were taking the derivative of an integral. Right? Derivative of an integral. And it got us back something having to do with the function, right? Something having to do with the function. Yesterday, with our Fundamental Theorem of Calculus Part 1, we were taking the integral of a derivative, weren't we? Integral of derivative, and that was f of b minus f of a. So again, it spat back out that function. Yeah? So that's how the two parts of the Fundamental Theorem of Calculus work. One is you're taking the integral of a derivative, and the other one is you're taking the derivative of an integral. Okay? And allows us to relate these things together. Okay. I'm wondering if I should go do examples or if we should just wait. I think I'm just going to wait and let's cover the rest of our material and then we'll do all the examples together. Okay? All right. Next up, in Unit 1, way back in Unit 1, first thing, well, not the first thing, but near the first thing that we did. In Unit 1, we learned that the average rate of change of f on a closed interval, let's call it a to b, the average rate of change of f on a to b was given by change in y over change in x, our general slope formula. Since our function is f, that would be change in f over change in x, because y is equal to f. Right? So change in f was f of b minus f of a. Change in x was b minus a. So this gave us our average rate of change of f. Right? Okay. But now we know something else. We know that f of b minus f of a is equal to the integral from a to b of what? F prime. First fundamental theorem, right? We did that yesterday. First fundamental theorem. So I can replace this numerator with this integral. So therefore I get the average rate of change of f on a to b is the integral from a to b of f prime of x dx over b minus a. Okay, with me so far? Doing good. All right. Now, I want to ask you, what is the rate of change of f? Rate of change of f. Rate of change of f is f prime. That is f prime, or f prime of x. So I could write this as the average f prime of x on a to b is equal to, and if I wanted to, I could pull this denominator and make it a coefficient. Like that. So the average f prime on a to b is 1 over b minus a times the integral from a to b of f prime. Now that I have it written like this, I can really generalize. Let's call f prime equal to g. If I did that, I would have the average g of x on a to b is 1 over b minus a, integral a to b of g of x dx. I could do the same thing with h of x. Average h of x on a to b would be 1 over b minus a integral a to b of h of x. And in general, we can say the average f of x on a to b is 1 over b minus a integral a to b of f of x dx. The average value of f, think about what that means. The average function value, this is the average y value, is equal to this. It's the average value of the function. This notation is generally accepted for the average value of f. The average value of f on a to b is equal to this expression. Average value of a function. Always on the AP exam. At least once. Okay? So let's think about this. When you're finding the average value of a function, your function is right there. Okay? This is not f prime in here. It's the function. The only time that would be f prime is if you were finding the average f prime. Okay? Now, how do you remember this? Well, here's how I tell kids to remember this. If I asked you to give me your average test score, let's say that we've taken 3 tests, and I ask you, what's your average of your test scores? What's your average grade? What would you do? What would you do with those 3 scores? Wouldn't you add them up first? You would add up your 3 test scores, wouldn't you? What does what does that integral sign mean? It means a sum, right? You're adding up your f's here, okay? You're adding up your test scores. You're adding up whatever you're trying to find the average of, right? If I asked you to give me the average of your test scores, you would not begin by adding up your quiz scores, right? Or your homework scores. You would begin by adding up your test scores. So if I ask you for the average f, begin by adding up all your f's, all right? So you would add up all your tests, and then you would divide by the number of tests, right? In this case, 3. Well, we're dividing by, essentially, b minus a, okay? But it makes sense that you would be dividing by something here. That's how I tell kids to remember it. Add up your function. Divide by b minus a. Okay? All right. Time for examples. Let me grab my examples here. I actually typed these up for you. You should have this, hopefully. Have this. Okay? These are the examples. So let's start with this one here. Okay, we've got the derivative of an integral. Derivative of an integral, think. Fundamental theorem. Part 2. Okay? I start at the top and take the derivative. Derivative of x is just 1. So I'm going to put 1 here, but since it's just a 1, you don't have to put that, right? And then substitute in x for every t in the function. So 1 plus x squared. Go to the bottom. Take the derivative. Derivative of 3 is 0. So we can just stop there. This is our answer. If we had a multiple choice, it would be 1 plus x squared. That would be the answer. Square root of 1 plus x squared. Number 2. Start at the top. Take the derivative. What's the derivative of natural log x? That's 1 over x. Take the derivative. Then plug it in for every t in the function. Tangent of natural log x minus the derivative of 4 is 0. So you don't have to put that there. And remember, this is only true because derivative of an integral. Fundamental theorem. Okay. Next up, number 3, derivative of an integral. Start at the top, take the derivative, 3x squared. Now plug in 3x squared for every t in the function. 1 over 1 plus x squared, x cubed. I think I said that wrong. You were plugging in x cubed for every t in the function. I think I said that wrong. Okay. Minus, now go to the bottom, take the derivative. Derivative is 1. Now plug in x for every t in the function. And then if you need to simplify, simplify. But that would be our safe stop answer. 3x squared over 1 plus x cubed minus 1 over 1 plus x. Okay? Number 4. Again, derivative of an integral. Fundamental theorem. Part 2. Start at the top. What's the derivative of negative 2? 0. Minus. Now go to the bottom. What's the derivative of cosine x? Negative sine x. Negative sine x. Now plug in cosine x for every t. So we're going to have the cube root of 1 plus cosine squared x. Like that. That's it. Okay? Number 5. If g of x is equal to this integral, then what is g prime of x? Well, g prime of x comes from taking the derivative of g, so we would be taking the derivative with respect to x of this integral. And what is the derivative of this integral? Well, that's second fundamental theorem of calculus, part 2. Okay? So derivative of x is just 1. Plug in x for every t in the function. Minus the derivative of 1 is just 0, so we don't have to even go there. So here, g prime of x is equal to f of x. The derivative of g is equal to f of x. Okay? All right, number 6. Find the average value of g of x on this interval. Formula time. Think. When you're finding the average of something, you add up all your things and then divide by how many there are, right? So for notation's sake, I'm going to call this, I'm going to do g average like that on the interval 1 to 4. So this is equal to 1 over b minus a. What is b minus a? 4 minus 1, or 3. Integral. Okay, are we going to put g prime here or g? If I ask you to average your tests, will you begin by adding up your tests or your quizzes? Your tests, right. So you find the integral of g. So 3x squared minus 2x from 1 to 4. Okay, dx. So this will be 1/3. Now antiderivative time. So x cubed times 1 minus x squared times 1. Evaluated from 1 to 4. This is 64 minus 16 minus, now I plug in the 1 minus 1. That would be a safe stop spot. 64 minus 16 is 48. 1/3 of 48 is 16. That would be the multiple choice. So this would be a safe stop. This would be the multiple choice answer. Okay? Number 7. At what value of x does f of x equal the average value? of f of x on the interval 0 to 3? Well, first let's find the average value of f on the interval. So the average value of f on the interval 0 to 3 will be 1 over 3 minus 0 times the integral from 0 to 3 of f of x dx. So this is 1/3 antiderivative time. This is 9x minus 1/3 x cubed from 0 to 3. I like having that 0 there, but we're going to start up at the 3. 3 times 9 is 27, minus 3 cubed over 3 is 3 squared, minus, when we put 0 in, we just get a 0. That would be a safe stop, but not multiple choice. Let's simplify for multiple choice. 1/3 of 27 minus 9 is 18, and 1/3 of 18 is 6. Okay? Oh, I should not have boxed that. Forget that I boxed that, because that's not my answer. Because that's not what we're trying to find. We want to find the value of x that makes f equal that average. So we're not done yet. Okay? We need to find the value of x that makes f of x equal 6, the average value. Right? So we're setting f equal to the average value. X squared will be 3, and x will be plus and minus square root of 3. Now we're done. We were almost done when we found that 6, but not quite. Okay, number 8. This one we get to use our calculator. And it says, at what value of x does h of x equal its average value on the interval 1 to 2 if h is equal to 1 over x cubed? Okay? So similar to the last example. Let's begin by finding the average of h on 1 to 2. So that will be 1 over 2 minus 1, or 1, integral 1 to 2 of h. Okay? And we get to use our calculator, so let's grab your calculator here. And this coefficient ends up just being a 1, so we don't have to put that in. Math 9 for the integral, 1 to 2, 1 divided by x cubed dx. So that will give us the average h. So that is 0.375. Okay? Now we want to find the x value at which h is equal to that. So I need to set h, I'm setting h equal to my average value and finding what x is. Okay, well, x cubed here would be 1 over that decimal, so x would be the cube root, x would be the cube root of 1 over 0.375. That would be a safe stop spot. As a multiple choice, though, we would need to go ahead and work that out. So 1 divided by 0.375 raised to the 1/3 power, because that cube root is 1/3 power, right? So 1.387. That would be the multiple choice answer. Okay, number 9. Find the value of k such that the average value of f of x, which is sine x, on the interval 0 to k is 2 over pi. Well, let's set up this expression for the average value. Average value will be 1 over k minus 0, integral 0 to k of the function. And that will equal, they're telling us what the answer is. The answer is 2 over pi. So now we just have to find k, right? So 1 over k the antiderivative of sine x is negative cosine x, right? Because the derivative of negative cosine x is sine x. And then we want to evaluate that from 0 to k. That has to be 2 over pi. Plug in your k first. So we'll have negative cosine k minus, now plug in 0 for x. Cosine of 0 is 1, but this is a negative 1, so that makes this a positive 1. Watch your signs there. Okay. So if we go ahead and distribute this 1 over k through, this would be 1 over k minus 1 over k cosine k. I think I'm going to bring that 2 over pi to the left-hand side is equal to that. How do we solve this for k with a calculator? Well, we can go and graph it. We can graph this side, right? Graph this side and just find out where that function is 0. So we've got one, I'm going to put in x for k, right? So 1 over x minus 1 over x times cosine of x minus 2 over pi. Okay? All right. And since we're on an interval 0 to k, I'm going to, I'm just going to do zoom 4, see what happens here. Okay. Now you might want to play around with this, change your window a little bit, see what's going on, but I do see these 2 values over here. And I'd like to go grab those 2 values. So I think I'm going to come back, and in for y2 I'm going to put 0, that way I can use intersection. Then second calc, intersect, enter, enter, enter. Oops, I think I should get over here. Enter, enter, enter. So my first k value here that makes this true is 1.5707963. Okay, which we could leave like that or round to 3 decimal places. That's fine. That does look familiar to me. I hope it looks familiar to you. Let's go grab the other k value. Enter, enter, enter. If the 1.570 number did not look familiar, I'm hoping this one does. 3.1415927 ... Okay, so these would be our answers, and that's fine to leave it like that, but the exact answers are pi over 2 and pi. Okay? All right, now this is an example of an FRQ, an AP FRQ. Okay, we are finally at a point where we can have an AP question, FRQ question, that is really exactly like what you would get on the exam. Okay, so this I think is a first for us, where we have an entire problem. All right, so let's take a look at it. It says the graph of a function f on -1 to 5 consists of a quarter circle and 3 line segments as shown on the right. That's on the right, but yes, okay, whatever. Let G, they always do it above. They always put their graph above, but it takes up a lot of space that way. Anyway, let G be the function given by this. Okay. Now, all of the questions in here are going to deal with G, not F. Your graph is of F. All your questions are about G. So we need to relate G with F, and this is how G is related to F. Okay? Now, since all of our questions are going to deal with G, at some point we're going to have to say what G prime is and what G double prime is. I encourage you to do it first thing at the beginning. They almost always give you space up here. So first thing, before you even get to your questions, go ahead and find G prime. and G double prime. Okay, so what is G prime of x? Well, G prime of x will be the derivative of G, and G is this. How do we take the derivative of an integral? That's the fundamental theorem part 2, right? So this is just f of x. So G prime of x is f of x. G double prime of x then is f prime of x, or the slope of f. Okay? So over here where they gave us the graph of f, since f is equal to G prime, this is also the graph of G prime. Okay? Alright. Part A. Find G of 0, G of -1, G of 2, G of 5. Do you remember that other, we did another problem similar to this with fundamental theorem of calculus part 1, okay? So likely we're going to be using these values later in this problem, okay? So let's start off, find G of 0. To find G of 0, you go to your G function because there's no derivative on this, right? Kids always want to go to this one because it's easier. Go to the one where you have to go because you would not plug in 0 for the function that you're not on, right? So we have to go up here, and you're plugging in 0 for x, right? Which means you're plugging in 0 for x. So this would be the integral from 0 to 0 of f of t dt. Well, the integral from 0 to 0, remember the property with the boundaries the same? This is just 0. Okay? Now let's go on to G of -1. Well, G of -1, we're plugging in -1 for x. So we plug in -1 for x. Everything else stays the same, just -1 for x. All right? Now for this integral, this is the area under the curve, right? This deals with the areas. But first thing I notice is that my -1 is smaller than my 0, so I need to switch those. Well, we can't just go switch those. We have to make it a negative integral, right? Now I can look at this as the negative area. Okay? So this is going to be negative area from -1 to 0. -1 to 0 is right here, this little triangle. So 1/2 base times height, like that. That would be a safe stop spot. But again, I'm pretty sure I'm going to be using this later, so while I'm here, I'm going to go ahead and simplify. It's easy enough to simplify. Okay? Go on to the next one, G of 2. Okay? G of 2, put 2 in for x, which means put 2 in for x. I say that because for some reason kids just want to go nuts and put 2 in for other things, and I don't understand why. But anyway, 2 in for x. Now this is just area from 0 to 2, right? So 0 to 2 is right here. It's above the x-axis, so this integral will be positive. It's all above the x-axis. Integral is positive. Positive of that area. And it's a quarter of a circle. Then we know that because they tell us. It doesn't just look like a quarter circle, it actually is a quarter circle. So quarter circle, so 1/4 pi r squared. R is 2. The radius here is 2. So this will be just pi. This would be my safe stop. This would be my simplification that I might need later. Okay? Next up, G of 5. Well, for g of 5, we have to put 5 in for x. So this will be integral 0 to 5 f of t dt. Area 0 to 5. Well, from 0 to 5, part of my area is above and part is below. So I'm going to split this up into pieces. So the part above was the pi that I got in my previous problem. Now this next section is going to be negative, right? I'm going to split this up. So I'm going to do this triangle right here. That's 1/2 base times height, 1 times 2. And then I'm going to come over here. And I could do this different ways, but I'm going to do this by using a trapezoid. This is I see a trapezoid here. The height is 2 of the trapezoid, so it's still below the x-axis, so it's still going to be negative. 1/2, the height there is 2, and the base lengths are 2 and 1. Some people say, Miss Murray, you can see that that's 1, 2, 3 units. I'm like, yeah, if you can see that, great. It's a little bit, this piece down here is a little awkward to me, so I wanted to make sure I knew what I was doing there. So that would be my safe stop spot. But again, I think we're going to be using this, so I'm going to simplify. So this is -1, -3, so this is pi minus 4. Okay? So on these, we're using the area under F because of the definition of G. Okay? Part B. Find all the values of x in the open interval -1 to 5 at which G has a relative max. Justify your answer. Well, think to your, here's my thought bubble. Thought bubble. Thought bubble is G prime needs to go from positive to negative. Okay? That's my thought bubble for a relative max for G. G has a relative max when G prime goes positive to negative. That's my thought process. Here's my graph of G prime. So where does G prime go from positive to negative? G prime is positive here and negative here. So G prime goes from positive to negative at x equals 2. So my response will be G has a relative max at x equals 2 since G prime goes from positive to negative there. For me, you can abbreviate your words, okay? If this was an AP exam, don't abbreviate, okay? Just go ahead and write it out. If you misspell something, it's okay, but just go ahead and write it out. Leave no question that you knew what you were doing, okay? Now, at this point, since we used G prime, somewhere above, we must have defined what G prime is. Okay? We did that way up here. We said what G prime was. If we had not said that here, we would have had to say that before we stated anything using G prime. Okay? We would have had to say G prime is equal to F here. Okay? Because in the problem so far, there's nothing about G prime. If we hadn't said that, or that, there's nothing given in the problem about G prime. So you have to say what G prime here in order to get credit for this answer. Okay? Part C, find the absolute minimum value of G on that closed interval and the value of x at which it occurs. Well, I see absolute min, and my thought bubble says closed interval test. Closed interval test. That's my thought bubble. So x, and then whatever we're finding the minimum of, we're finding the minimum of g. Okay? Start with your closed interval, -1 and 5. Those are your boundaries, your intervals. And then remember, we need anything that makes g prime 0 or g prime undefined. Okay? So g prime is 0. G prime is 0. Here's the graph of G prime, and G prime is 0 right here, isn't it? G prime is 0 at x equals 2. And no other value, except for a boundary, right? No other value. Okay? So here, we found several values, and that's the only value that makes g prime 0. So we found several g values, right? Did we find g of -1? Yes, we did. We found g of -1. That's a -1. Did we find g of 5? We did find g of 5. G of 5 was pi minus 4. Did we find g of 2? We sure did. G of 2 is pi. Okay? So we can say with no doubt that G has an absolute minimum value of, which is lower, -1 or pi minus 4? Which is lower? Pi is about 3.14, yeah? 3.14 minus 4 will be bigger than a -1. So the absolute minimum value will be -1 at x equals -1, which they do tell us we have to say this time. If you want to say by closed interval test, fine. But you don't have to, because the closed interval test is staring at me in the face. So you don't have to. That's it. FYI, you guys, this 2 here, was there any way that that could have been an absolute minimum? We just got done saying that x equals 2 was a relative maximum of g. So would there be any way that that 2 would be an absolute minimum if it was at a relative maximum? No. It would. There's no way. Okay? So from the get-go, I knew that the absolute min had to be at either one of these boundaries. D. Find the x-coordinate of each point of inflection of the graph of G on -1 to 5. Justify your answer. So thought bubble, point of inflection of G, thought bubble, point of inflection of G is where G double prime changes signs, right? That's what I'm thinking. I need G double prime to change signs. Since I'm going to be using G double prime, somewhere in the problem I had to say what G double prime was, right? G double prime is the slope of f. It's the slope of this graph. So we're looking for, where does the slope of this graph change signs? The slope of the graph change signs. Well, here the slope is positive. Here the slope is negative. So x equals 0, not x equals 2, x equals 0 is where the slope changes signs. Okay? Does the slope change signs here? No. It goes from negative to negative. Does the slope change signs here? Yes. The slope goes from negative to positive. So here G has 2 points of inflection. X equals 0 and x equals 3. let's write that. G has a point of inflection at x equals 0 and x equals 3, since G double prime changes signs there. And again, somewhere, since we used G double prime here, somewhere above, or right here, somewhere, if we hadn't done it up at the top, somewhere above, we must have said what G double prime is. Okay? You can't use G double prime without saying what it is. You can't use G prime without saying what it is, unless it's given to you in the problem. Okay? Kind of makes sense. Okay, that was a great FRQ. Another thing that they could have asked. Let's add a part E here. Find G double prime of, let's find G double prime of 4. G double prime of 4. Okay. Well, remember, G double prime of 4 is the slope of G prime at x equals 4, right? And G prime is up. So we want the slope right here. We want the slope right here. What is the slope right here? Well, it's up 1 over 2, so it's 1/2. So G double prime of 4 is 1/2. It's the slope there. Okay? What about G double prime at, let's find G double prime at 2. G double prime at 2. Well, what's the slope here? The slope there does not exist, because the slope from the left is not equal to the slope from the right. They're not equal. It's a cusp, right? So G double prime at 2 does not exist, since G prime has a cusp at x equals 2. Okay? Anyway, what I did in this was I gave you 4 problems, but they could give you several different kinds here, including something about finding G double prime. Okay? Alright. Fun stuff. I love this whole unit. It's so important. We're getting to where we can do full FRQs, so that's fantastic. Okay, go try it on your own now, guys.